There's something out there that shouldn't know how to do what it's doing. 3I Atlas, an interstellar visitor from beyond our solar system, has spent the last month performing an impossible trick. It's switching itself on and off like a machine following a schedule. November 5th, dormant. November 16th, blazing. November 26th, silent again. December 2nd, active. December 8th, off. 5 perfect cycles in 33 days. Comets don't do this. Rocks heated by the sun don't pulse on command. But this object does, and we've documented every single activation. Stay with me until the end, because what we've discovered about the timing of these cycles changes everything we thought we understood about what's possible in deep space. Stay tuned, because 3I Atlas remains under observation right now, with instruments locked onto its position as it drifts farther into the dark. Hit subscribe to stay connected to this unfolding enigma, because whatever happens next could rewrite our understanding of what moves through the space between stars. You're looking at something that shouldn't exist. Not according to the rules we've spent centuries building. Not according to the laws of how ice and rock behave when they're hurtling through the void. But there it is, captured in frame after frame from telescopes across the planet and beyond, doing the one thing a comet absolutely cannot do. It's switching itself on and off like a light bulb. This is 3I Atlas, an interstellar visitor that entered our solar system from the infinite dark between stars. When astronomers first spotted it, they cataloged it as another comet, another chunk of ice and dust wandering through our neighborhood on its way to somewhere else. They expected it to follow the script. Comets have a script. They get bright as they approach the sun, then they fade as they leave. It's thermal physics, simple as turning on a stove. Heat goes in, gas comes out, brightness follows a predictable curve. 3I Atlas was supposed to dim gradually as it moved away from the inner solar system after its closest approach. Instead, it started flickering. The timeline reads like a malfunction report, not an astronomical observation. November 5th, 2024, the comet goes dark, dormant, silent, like someone flipped a switch. Then November 16th arrives, and suddenly it's blazing again. Activity everywhere. The coma, that fuzzy cloud of gas and dust surrounding the nucleus, lights up in a riot of color. Jets spray outward in directions that make no geometric sense. Observers scramble to record it, because this isn't supposed to happen. But they're recording it anyway, because it is happening. November 26th, off again, just like that. The show stops. 3I Atlas returns to being a cold, inert rock drifting through space. No warning, no gradual fade, it just stops. Then December 2nd rolls around, and the comet wakes up. On, active, glowing, jets, firing. And then December 8th arrives, and silence returns. Off. 5 distinct phases in the span of 33 days. Dormant, active, dormant, active, dormant. This isn't a thermal curve. This is digital behavior. Binary, 1 or 0, on or off. Imagine standing in a field at midnight and watching a distant star pulse in a pattern. 3 seconds on, 5 seconds off, 3 seconds on again. You wouldn't think interesting atmospheric conditions. You'd think someone's sending a signal. That's the kind of pattern we're seeing here, except stretched across weeks instead of seconds. And the object in question is a comet that's supposed to be governed by nothing more intelligent than physics. Natural outgassing doesn't work this way. When sunlight heats a comet's surface, ice sublimates into gas. The process is gradual because heat diffusion is gradual. You don't get sudden jumps. You don't get perfect dormancy, followed by explosive activity, followed by perfect dormancy again. It would be like boiling water that refuses to form bubbles until the temperature hits exactly 100 degrees Celsius, then instantly erupts into steam, then goes completely still the moment you remove 1 degree of heat. Water doesn't do that. Ice doesn't do that. Rock doesn't do that. But 3i Atlas does. The visual data makes it even stranger. When the comet is active, it's not just bright, it's chaotic. Multiple jets erupt simultaneously, shooting material in directions that don't align with the simple geometry of solar heating. A normal comet rotates, and that rotation smears its jets into beautiful spiral patterns as material streams away from specific vents on the surface. You can predict where the jets will point based on which way the nucleus is facing and where the sun sits in the sky. 3i Atlas produces jets that look less like organized venting and more like a machine misfiring in multiple directions at once. Some observers have described it as a comet with a heartbeat. That's not scientific language, but it captures something the data struggles to convey. There's a rhythm here, a cycle, and cycles imply systems. Systems imply organization. Organization implies something we're not supposed to find on a frozen rock that's been tumbling through interstellar space for who knows how many millions of years. NASA released new images. The European Space Agency released new images. Ground observatories released new images. Every time 3i Atlas switched on, someone was watching, and every image confirms the same impossible story. This object is doing something no comet should be able to do. It's controlling its own activity. The question lands like a weight in your chest. Why would an inert rock turn itself on and off? What mechanism could possibly create this pattern? Solar heating is ruled out because the pattern doesn't correlate with distance from the sun. Rotation is ruled out because the timing doesn't match any reasonable spin period. Outgassing pressure is ruled out because outgassing doesn't start and stop on a schedule. Every natural explanation runs into the same wall. The behavior is too precise, too regular, too deliberate. This isn't just new science. This might be something that forces us to rewrite the rules entirely. Because if 3i Atlas isn't behaving like a comet, then maybe it isn't a comet. And if it isn't a comet, then we need to start asking much harder questions about what it actually is and where it came from and whether the universe is stranger than we've been willing to admit. The observations are continuing. The pattern is continuing. And somewhere out there, beyond Mars, moving away from the sun on a trajectory that will eventually take it back into the void between stars, 3i Atlas is either about to switch on again or it's already decided to stay silent. Either way, we're watching, and we have no idea what we're watching anymore. The tracking started long before anyone realized they were watching something impossible. 3i Atlas was first detected in 2024 as it approached the inner solar system, and from that moment forward, it became one of the most closely monitored objects in recent astronomical history. NASA's network of ground-based telescopes picked it up. The European Space Agency's observatories locked onto it. Even spacecraft near Mars, equipped with cameras meant for other missions, turned their lenses toward this visitor as it passed through our neighborhood. What began as routine observation of an interstellar comet turned into something else entirely when the data started coming back. The Hubble Space Telescope captured images that stopped astronomers cold. The coma was larger than expected, brighter than expected, and the structure within it was complex in ways that simple sublimation couldn't explain. Comets are supposed to be messy, but predictable. Gas and dust stream away from the nucleus in patterns dictated by rotation and solar radiation pressure. What Hubble saw looked less like organized streaming, and more like explosive venting from multiple sources that didn't correlate with any obvious surface features. The nucleus itself remained difficult to resolve, buried within all that activity. But the coma told a story of energetic processes happening on a scale that didn't match the object's size or expected composition. Ground-based optical tracking added more pieces to the puzzle. Lowell Observatory's Discovery Telescope in Arizona caught 3i Atlas after it emerged from behind the sun, when solar glare no longer blocked the view. The observations confirmed what space-based instruments had already suggested. This wasn't a faint, dying comet on its way out of the solar system. This was an object that refused to follow the brightness curve everyone had calculated. It should have been fading steadily as it moved farther from the sun's warmth. Instead, it pulsed, it surged, it went quiet, then roared, back to life without any obvious external trigger. Spectroscopic analysis revealed another layer of weirdness. When astronomers break down the light coming from a comet, they can identify which gases are present in the coma by looking at specific wavelengths. Every molecule absorbs and emits light in its own unique pattern, like a fingerprint. 3I Atlas showed fingerprints that didn't match the typical comet profile. The ratio of carbon dioxide to water was unusually high. Most comets are dominated by water ice, with carbon dioxide playing a supporting role. This one seemed to reverse the formula, or at least skew it heavily toward carbon dioxide in a way that raised immediate questions about where it formed and under what conditions. Water outgassing was still present, detected through emissions from hydroxyl radicals, the molecular fragments that appear when water molecules break apart under solar ultraviolet radiation. But the quantities didn't align with the brightness spikes. You'd expect more water vapor during the active phases, following the simple logic that more activity equals more sublimation. The measurements suggested something more complicated was happening. Either the ice composition was wildly different from solar system comets, or the activity wasn't being driven by ice sublimation at all. The dust tail added yet another complication. Comets produce two tails, an ion tail made of charged particles blown back by the solar wind, and a dust tail made of solid grains pushed by radiation pressure. 3I Atlas developed a dust tail that was both more prominent and more variable than models predicted. The dust grains themselves, analyzed through polarimetry, showed properties that didn't quite match standard cometary dust. The scattering patterns suggested either unusual composition or unusual size distribution, or both. In simpler terms, the dust coming off this object looked different from the dust coming off other comets, and nobody could immediately explain why. All of these measurements paint a picture of an object that's chemically distinct, behaviorally anomalous, and structurally complex. If 3I Atlas had followed the predicted path, it would have been a minor curiosity, another data point confirming what we already knew about interstellar comets. Instead, it became a problem. A fascinating, infuriating problem that refused to fit into any of the existing categories. The data is good. Multiple independent observatories using different instruments and techniques all confirm the same basic facts. This isn't an error. This isn't a misidentification. This is real behavior from a real object, and it contradicts nearly everything cometary science has established over the past century. The tension between observation and theory creates a space where speculation rushes in to fill the gaps. Professional astronomers, trained to be cautious and methodical, focus first on finding natural explanations. Maybe the composition is so unusual that it produces these rapid activity cycles through some unknown chemical reaction. Maybe the surface structure is honeycombed with vents that open and close based on thermal stress. Maybe there's a subsurface ocean of volatile compounds that occasionally breaks through the crust in violent outbursts. These are all plausible ideas that don't require throwing out physics, but they're also ideas that strain credibility when you look at the actual timeline of activity. The pattern is too clean, too regular, too much like someone flipping a switch. Which brings us to the hypotheses that make scientists uncomfortable and audiences excited. If thermal sublimation can't explain the on-off cycling, what can? One line of speculation focuses on propulsion-like behavior. The idea here is that the activity resembles controlled thrusting rather than passive venting. A rocket engine fires in short bursts to adjust trajectory. What if 3I Atlas is doing something similar? Not because it's designed to, but because of some natural process that mimics propulsion. Or, more provocatively, What if it actually is designed to? Another hypothesis suggests discrete energy cycles. Instead of a comet that's passively responding to sunlight, imagine an object that's actively managing its energy budget. It powers up, performs some function that requires releasing gas and dust, then powers down to conserve whatever energy source it's using. This sounds like describing a machine, and that's the point. The behavior looks more mechanical than geological. It's the difference between a geyser that erupts whenever pressure builds up and a sprinkler system that turns on at scheduled intervals. Then there's the timing question. Does the pattern correlate with anything external? Position relative to planets, intensity of solar radiation, magnetic field strength. Some researchers have suggested that 3I Atlas might be responding to environmental triggers we haven't identified yet. But that just pushes the mystery back a step. Why would a comet have a mechanism sophisticated enough to detect and respond to subtle environmental changes? What evolutionary or geological process would build that kind of sensitivity into a frozen rock? These hypotheses aren't supported by peer-reviewed evidence yet. They're exploratory ideas that scientists discuss in conference hallways and email threads, trying to make sense of data that refuses to make sense. The astronomical community is split between skepticism and curiosity. Some dismiss the whole thing as overinterpretation of noisy data. Others admit quietly that they don't have a good natural explanation, and maybe it's time to consider stranger possibilities. And that's where we're headed next. Into the controversies. Into the debates that are happening right now about what 3I Atlas actually is, and what it means if we can't explain it away. The physics don't add up, and that's where things get interesting. When you strip away the technical jargon and the careful hedging of scientific papers, what you're left with is a simple problem. 3I Atlas is exhibiting behavior that standard cometary physics cannot easily accommodate. The question is whether that means we're seeing new physics or whether we're seeing something that was never governed by natural processes in the first place. Start with the jet structures. Comets rotate, typically with periods ranging from hours to days. As the nucleus spins, active areas on the surface trace out spiral patterns in space, like water spraying from a rotating lawn sprinkler. The jets appear to curve because the source is moving as material streams away. This is textbook cometary behavior, observed hundreds of times across dozens of different objects. 3I Atlas produces jets that don't follow this pattern. Multiple directions, simultaneous eruptions from locations that don't align with any single rotational axis. Some observations show jets firing almost perpendicular to each other, which would require either an extremely complex rotation state or multiple independent sources of activity that just happen to fire at the same time. The rotational smearing that should be visible isn't there, or rather, it's inconsistent. Sometimes the jets look organized. Sometimes they look chaotic. Sometimes they appear, disappear, and reappear in completely different orientations over timescales too short for the rotation period to account for the changes. It's like watching a fountain that keeps moving its nozzles around while you're looking at it. Natural objects don't do that. They have fixed geometries. Active regions stay in the same place relative to the nucleus. Jets emerge from those regions and create predictable patterns. Unless something is fundamentally different about how this object is structured or what's driving the activity, the observations don't fit the model. Polarimetric measurements add another dimension to the mystery. Polarimetry measures how light waves are oriented after they scatter off particles. Different materials and different particle sizes produce different polarization signatures. 3I Atlas shows polarization patterns that suggest unusual dust properties. The grains might be more irregular than typical cometary dust. They might have different compositions. They might be coated in something that changes how they interact with light. Studies using spectropolarimetry have documented these anomalies in detail, comparing 3I Atlas to other solar system comets and finding consistent differences that nobody can fully explain. The dust is weird. The way it scatters light is weird. And weird in astronomy usually means either we're missing something about the object or we're missing something about physics. Then there's the carbon dioxide problem. Most comets are water-rich because most of the solar system formed from a disk that was dominated by water ice in the outer regions. Carbon dioxide is present, but usually as a secondary component. 3I Atlas flips this ratio, or at least significantly elevates the carbon dioxide content. That suggests it formed in a region with different chemistry, possibly colder or richer in carbon-bearing compounds. Interstellar space has different conditions than the solar nebula. Different temperatures. Different abundances of various elements. If 3I Atlas really is an interstellar object, maybe its composition reflects wherever it came from rather than our local neighborhood. But that still doesn't explain the on-off cycling. Unusual chemistry doesn't create unusual timing. You can have all the exotic volatiles you want, and they'll still sublimate in response to heat, according to the same thermodynamic principles that govern everything else. None of these anomalies alone proves anything extraordinary. Taken together, though, they create a picture of an object that doesn't fit comfortably into existing categories. It's compositionally distinct, behaviorally anomalous, structurally complex, and it's doing all of this while following a pattern that looks less like geology and more like engineering. Which brings us to the part where the conversation gets uncomfortable. Extraordinary claims attract extraordinary scrutiny, and 3I Atlas has attracted both. The mainstream skepticism focuses on observational effects. Maybe the pulsing is an optical artifact caused by changing viewing geometry. As the comet moves and Earth moves, the angle we're observing from changes continuously. Maybe what looks like activity cycling is actually just us seeing different parts of the nucleus at different times, with some regions being naturally more active than others. It's a reasonable hypothesis. It's also hard to square with the fact that multiple independent observatories using different instruments and different viewing angles all report the same basic pattern. Artifacts are usually instrument-specific. What we're seeing is object-specific. Photometric errors are another possibility. Maybe the brightness measurements are unreliable. Maybe atmospheric conditions or telescope calibration issues are introducing noise that looks like a pattern. Again, plausible. But the pattern persists across different observation campaigns, different telescopes, different analysis methods. At some point, you have to accept that the pattern is real and stop looking for ways to explain it away as measurement error. Non-gravitational acceleration is where the debate gets technical and heated. Some comets experience tiny changes in their orbits caused by outgassing. The gas streaming off the surface creates a small rocket effect that gently nudges the comet off its purely gravitational trajectory. Detecting this effect requires extremely precise measurements of the comet's position over time. For 3I Atlas, some studies claim little to no detectable non-gravitational acceleration, which would be weird if the object is producing significant outgassing during its active phases. Others argue that any acceleration might be masked by the comet's trajectory or by the timing of observations. If the thrusting happens in directions that largely cancel out, or if we're not measuring frequently enough to catch the changes, we might miss it entirely. The debate continues, with different teams analyzing the same data and reaching different conclusions. More provocative hypotheses have started appearing in public discussions, though not yet in peer-reviewed journals. Some researchers have begun floating the idea that 3I Atlas might be exhibiting evidence of technological control. Not natural processes that mimic technology, but actual technology. Propulsion systems, navigation systems, energy management systems. These suggestions appear mostly in interviews, social media posts, and conference talks rather than formal papers, which tells you something about how the scientific community views them. They're interesting, they're worth discussing, but they're not yet backed by the kind of evidence that would survive peer review. That doesn't make them wrong. It makes them unproven And in science, unproven ideas exist in a liminal space between possibility and speculation, waiting for either confirmation or refutation. Different camps have emerged. Conservative astrophysicists argue that we simply need better models of exotic cometary behavior, and that invoking artificial origins is premature and unnecessary. Fringe theorists argue that the evidence already points towards something non-natural, and that mainstream science is too cautious to acknowledge what's right in front of us. The truth, as usual, probably lives somewhere between these extremes. 3I Atlas might be a natural object doing natural things we don't understand yet. Or it might be something else. The challenge is distinguishing between what we know, what we suspect, and what we're afraid to consider. Because if the natural explanations genuinely fail, then we're left with a much stranger universe than the one we've been studying for the past few centuries. And that possibility is simultaneously thrilling and deeply unsettling. Let's follow the logic to its uncomfortable conclusion. What if the natural explanations genuinely fail? Not because we haven't looked hard enough or measured precisely enough, but because the object in question isn't natural. What does that scenario look like? And what would it mean for everything we think we understand about our place in the universe? The artificial object hypothesis starts with a simple premise. If 3I Atlas is exhibiting controlled behavior, then something is controlling it. That something could be internal mechanisms, systems designed and built by an intelligence that predates human civilization by an unimaginable span of time. The idea sounds like science fiction until you remember that humanity itself has already sent artificial objects into interstellar space. Voyager 1 and Voyager 2 are currently beyond the heliopause, drifting through the space between stars on trajectories that will eventually carry them to other stellar neighborhoods millions of years from now. Any civilization encountering those probes in the distant future would recognize them as engineered artifacts. They have structure, purpose, technology. 3I Atlas might be the equivalent from someone else's history, a probe or spacecraft or piece of infrastructure that outlived its creators and now wanders through the galaxy on autopilot. What would such an object look like after millions or billions of years in the void? It wouldn't be gleaming metal and pristine circuits. Interstellar space is not empty. Dust grains, ice particles, and cosmic rays would gradually erode and coat any surface exposed to that environment. An ancient probe might accumulate layers of frozen volatiles, making it visually indistinguishable from a comet until it activates systems that blast away the accumulated material. The on-off cycling could be periodic maintenance, self-diagnosis, attempts to communicate, or simply the operation of systems designed for purposes we can't fathom from the limited data we have. The object came from somewhere beyond our solar system, moving on a trajectory that didn't originate here. It passed through, possibly collecting data, possibly ignoring us entirely, and it will continue on its path until it enters another stellar system, or until its systems finally fail completely. The origin scenarios branch outward from there. An advanced extraterrestrial civilization might send probes as exploration tools, similar to our own space missions, but on a vastly larger scale. Instead of targeting specific nearby stars, they might carpet the galaxy with thousands or millions of autonomous probes, each one programmed to investigate any system it encounters. 3I Atlas could be one such probe, activated by its passage through the inner solar system, performing whatever scans or measurements its programming dictates before returning to dormancy to conserve energy for the next encounter. The timing of its activity might correspond to specific observational windows when Earth and other planets were in optimal positions for study. Or it might correspond to internal schedules that have nothing to do with us at all. Another possibility involves derelict spacecraft, not probes, but actual vessels designed to transport something somewhere, now adrift after their mission ended, or their crew perished, or their home civilization collapsed. The universe is old. Civilizations rise and fall. If intelligent life is common on cosmic timescales, then the galaxy might be littered with technological remnants from species that no longer exist. 3I Atlas could be a ghost ship, its systems still functioning on some minimal level, firing thrusters to maintain attitude or dump excess energy or correct trajectory drift. The behavior we're interpreting as mysterious might be perfectly routine operation from the perspective of whoever built it. More speculative still are scenarios involving natural interstellar engineering. Not technology in the sense of wires and computers, but large-scale structures or processes created by natural phenomena we haven't discovered yet. Maybe there are ways for complexity to self-organize in the voids between stars, producing objects that mimic design systems without ever involving conscious intention. This is essentially trying to have it both ways, acknowledging that 3I Atlas looks artificial while preserving the assumption that everything in the universe arises from natural processes. It's possible. The universe has surprised us before with emergent complexity that seems impossible until we understand the underlying mechanisms. But it's also a bit of a cop-out. If something looks designed and acts designed, maybe the simplest explanation is that it was designed. Comparisons with other interstellar visitors become inevitable at this point. 1I/Oumuamua was the first confirmed interstellar object detected passing through our solar system, arriving in 2017 and causing immediate controversy. It was elongated, tumbling, and exhibited non-gravitational acceleration that suggested outgassing despite the complete absence of any detectable coma or tail. Some researchers proposed it was a hydrogen iceberg, slowly releasing gas too diffuse to detect. Others suggested light sail technology, a thin reflective surface pushed by radiation pressure. The debate never reached consensus, and Oumuamua left the solar system before more detailed observations could be made. 2I/Borisov followed in 2019 and was boringly normal by comparison. It looked like a comet, behaved like a comet, and satisfied everyone's expectations. 3I Atlas sits somewhere between these extremes. More active than Oumuamua, stranger than Borisov, and with observational coverage detailed enough to rule out many of the explanations that worked for previous objects. The psychological implications are worth considering as well. If 3I Atlas really is artificial, then we're forced to confront the existence of other intelligences in the universe, not as abstract possibilities, but as concrete realities with technological capabilities. That civilization, wherever and whenever it existed, achieved spaceflight, built machines capable of crossing interstellar distances, designed systems robust enough to function for the eons it takes to travel between stars. And they did all of this before humans even existed as a species. The timescale is humbling. The technological gap is terrifying. We send probes to Jupiter and Mars and feel proud of our achievements. They apparently send probes to other stars as casually as we send satellites to orbit Earth. What else did they build? What else is out there, drifting through space, that we haven't detected yet? Even if 3I Atlas isn't artificial, the questions it raises remain valid. The universe continues to surprise us. Every generation of astronomers believes they've figured out the basic rules, and every generation discovers phenomena that don't fit those rules. Black holes were theoretical curiosities until we found them. Dark matter was heresy until it became consensus. Exoplanets were science fiction until they became routine discoveries. 3I Atlas might be the next step in that progression, the observation that forces us to expand our understanding yet again. Whether it's a new type of comet or an old type of spacecraft, it represents a challenge to our existing frameworks. And challenges, uncomfortable as they might be, are how science moves forward. So we keep watching, we keep measuring, and we prepare ourselves for the possibility that the answers we find might be stranger than any of the questions we thought to ask. Something else happened recently that adds another layer to this mystery. and it's the kind of detail that makes you stop and reconsider everything. 3I Atlas has been detected emitting X-rays. Not hypothetically, not theoretically. Actually detected by instruments designed to observe high-energy phenomena in space. This is the first time X-ray emissions have been confirmed from an interstellar comet, and it raises questions that go far beyond the pulsing activity we've already been struggling to explain. X-rays in space typically come from extremely hot objects or extremely violent processes. The sun emits X-rays from its corona, where temperatures reach millions of degrees. Neutron stars and black holes emit X-rays as they shred and consume nearby matter. Supernova remnants emit X-rays from shockwaves plowing through interstellar gas. Comets do not emit X-rays, or at least they're not supposed to. The only exception occurs when solar wind particles collide with cometary gas, a process called charge exchange that produces faint X-ray emissions. But those emissions are weak and diffuse, nothing like what's being reported from 3I Atlas. The detected signal is stronger and more structured, suggesting either an unusually intense charge exchange process or something else entirely. What makes an X-ray source unusual? In simple terms, X-rays are high-energy photons, and creating them requires high-energy processes. You don't get X-rays from cold objects or slow processes. You get them from particle accelerators, either natural or artificial. The solar wind charge exchange explanation assumes that fast-moving ions from the sun are stripping electrons from molecules in the comet's coma, releasing energy in the X-ray range as those atoms settle back into stable configurations. For this to produce detectable emissions, you need a dense coma and strong solar wind. 3I Atlas has both during its active phases, so the explanation is plausible, but it doesn't explain why the X-rays appear. To correlate with the activity cycling, if the emissions were purely from charge exchange, they should track solar wind strength and coma density in a continuous, gradual way. Instead, they seem to pulse along with everything else. Multi-band observations are reshaping how we understand small solar system bodies. Traditional astronomy focused on visible light because that's what our eyes see and what early telescopes could detect. Modern astronomy spans the entire electromagnetic spectrum, from radio waves to gamma rays. Each wavelength reveals different aspects of an object. Visible light shows us surface features and reflected sunlight. Infrared reveals temperature and thermal emission. Radio detects molecules and magnetic fields. X-rays probe the highest energy processes. By observing 3I Atlas across all these bands simultaneously, researchers are building a complete picture of what's happening moment by moment. And that picture keeps getting stranger the more data comes in. Let's step back for a moment and ground ourselves in something familiar. The Geminid meteor shower peaked just recently, right on schedule, exactly as predicted by decades of observation. The Geminids are caused by Earth passing through a debris stream left behind by an asteroid called 3200 Phaethon. Every December, our planet plows through this stream, and tiny particles burn up in our atmosphere, creating brilliant streaks across the night sky. It's predictable, it's beautiful, and it's completely understood. We know where the debris came from. We know why it's there. We know exactly when Earth will encounter it every year. The Geminids are comforting in their regularity, a reminder that some space phenomena follow clockwork precision and don't surprise us at all. 3I Atlas is the opposite of comforting. It refuses to follow the script. While meteor showers demonstrate that we've mastered the basics of orbital mechanics and debris dynamics, this interstellar visitor demonstrates that we haven't mastered everything. Not even close. The contrast is important because it shows that our confusion isn't from incompetence. We can predict meteor showers a century in advance. We can calculate orbital paths with absurd precision. We understand how comets work when they follow the rules. 3I Atlas just isn't following the rules, and that's a very different problem from not knowing the rules in the first place. The exoplanet revolution provides another point of comparison. In the 1990s, we knew of exactly one planetary system, ours. Today, we've confirmed thousands of exoplanets orbiting other stars, and we've discovered that planetary systems are wildly diverse. Hot Jupiters orbit closer to their stars than Mercury does to the Sun. Super-Earths exist in sizes we don't have in our solar system. Systems with multiple planets in tight resonances. Systems with planets in retrograde orbits. Systems that look nothing like the orderly arrangement we grew up learning about. The universe turned out to be far more inventive than we imagined. If planetary systems can be that diverse, why not the debris that orbits those systems? Why not the comets and asteroids and other small bodies that form wherever stars form? 3i Atlas might be showing us a type of object that's common elsewhere, but completely alien to our local experience. Brown dwarf discoveries have followed a similar trajectory. These objects, halfway between planets and stars, were predicted theoretically long before any were actually found. Now we know they're abundant, and we're discovering that they have their own weather patterns, their own magnetic fields, their own weird physics that doesn't quite match stars or planets. The universe keeps filling in categories we thought were empty, and revealing that the boundaries between different types of objects are much blurrier than our classification schemes suggest. Comets, asteroids, brown dwarfs, exoplanets, they all exist on continua rather than in neat boxes. Maybe 3i Atlas represents yet another point on a continuum we haven't fully mapped yet. Galaxy formation research has undergone similar revolutions recently. Observations from the James Webb Space Telescope have found galaxies in the early universe that are more massive and more structured than theory predicted they should be. The model said that galaxies should build up gradually over billions of years, starting small and growing through mergers and accretion. Instead, we're finding large, mature-looking galaxies less than 1 billion years after the Big Bang. This doesn't mean the Big Bang is wrong. It means our understanding of how galaxies form is incomplete. We're missing processes or timescales or feedback mechanisms that current models don't account for. And rather than being a crisis, this is an opportunity. Science advances by finding places where theory and observation disagree and figuring out what we got wrong. 3i Atlas fits into this broader pattern of the universe, proving stranger than expected. Every time we think we've got things figured out, something comes along that doesn't fit the paradigm. These aren't failures of science. They're the growing pains of a species trying to understand a cosmos that's vastly more complex than the tiny corner we evolved in. Whether 3i Atlas is a comet with unusual chemistry, or a probe from a dead civilization, or something else we haven't thought of yet, it's doing exactly what the best scientific puzzles do. It's forcing us to question our assumptions and expand our thinking. And that process, uncomfortable as it might be, is how we move from ignorance to understanding. Even if understanding means accepting that we share the galaxy with things we're not equipped to recognize yet. The larger questions loom over all of this, like shadows cast by a light we can't quite see. If 3i Atlas is artificial, we need to confront what that means, not just for astronomy, but for philosophy, for our understanding of life in the universe, for the story we tell ourselves about humanity's place in the cosmic order. If it's natural, we need to explain why a frozen rock is behaving like a machine, and what that tells us about physical processes we apparently don't understand yet. Either answer is uncomfortable. Let's start with the uncomfortable truth about interstellar travel. It's hard. Not, we need better rockets, hard. Laws of physics make this almost impossible, hard. The distances are so vast that even moving at a significant fraction of light speed, it takes years to reach the nearest star, and decades or centuries to reach anything farther away. And that's assuming you can achieve those speeds in the first place, which requires energy budgets that dwarf anything humanity has ever generated. For reference, Voyager 1 is traveling at roughly 17 kilometers per second, which sounds fast until you realize it would take over 70,000 years to reach the nearest star system if it were aimed in that direction. Which it isn't. Any civilization attempting interstellar exploration faces these same constraints. Physics doesn't care about technological advancement. You can't invent your way around the cosmic speed limit. You can't shortcut the energy requirements. What you can do is build for the long term. Autonomous probes that don't need life support. Systems robust enough to function for millennia without maintenance. Power sources that last for geological timescales. If 3i Atlas really is a probe, then whoever built it solved these problems in ways we're only beginning to imagine. They created something that could survive the crossing between stars and still function when it arrived. That's not just impressive engineering. That's a completely different category of technological achievement. The psychological profile of such a civilization becomes a fascinating thought experiment. Why send probes at all? Curiosity is one answer. The same drive that makes humans build telescopes and rovers and space stations. But curiosity at that scale implies patience and long-term thinking that's foreign to our experience. The builders of 3i Atlas, if it's a probe, would have known they'd never see the results. The probe would take thousands or millions of years to reach another star system. Any data it collected would take just as long to return, if it returned at all. You don't undertake projects like that unless your civilization thinks in timescales that make human history look like a brief flicker, or unless you've accepted that the project itself is the point, not the results. Humanity's own deep space probes offer a mirror for comparison. The Voyager spacecraft carry golden records, physical artifacts encoded with information about Earth and humanity. They're time capsules launched into the void with the slim hope that someday someone might find them and decode the message. We sent them knowing we'd never know if anyone received them. We sent them because the act of sending felt important. A gesture toward the future and the possibility of connection across the abyss of space and time. If 3i Atlas is similar, then we're on the receiving end of someone else's gesture. We're the aliens finding the probe. We're the ones trying to decode the message, assuming there is one. But maybe there's no message. Maybe 3i Atlas is just infrastructure, a navigation beacon or resource cache or data relay that serves a function we can't recognize because we're not part of the network it was built for. Imagine an ant colony discovering a cell phone tower. The tower clearly isn't natural. It's obviously built. But understanding its purpose would require understanding cellular networks and electromagnetic communication and the entire technological ecosystem the tower exists to support. The ants might notice that the tower occasionally emits signals, might even measure those signals, but they'd never grasp the full context because the context is beyond their conceptual framework. We might be in a similar position with 3i Atlas. We're detecting the signals, we're measuring the behavior, but we're missing the framework that would make sense of it all. 1i/Oumuamua sparked similar debates when it arrived in 2017. Its elongated shape, unusual trajectory, and non-gravitational acceleration all fueled speculation about artificial origins. The light sail hypothesis suggested it might be a thin, reflective object pushed by radiation pressure, either a natural formation or deliberately constructed technology. The debate was never settled. Oumuamua left the solar system before we could gather enough data to reach consensus, and it remains ambiguous. A tantalizing hint that we either don't understand interstellar objects as well as we thought, or that we've already encountered artificial ones without being able to prove it. 2I/Borisov, by contrast, was disappointingly normal. It looked like a comet from the Oort cloud, behaved like a comet, and reinforced the idea that most interstellar visitors are probably just icy debris ejected from other stellar systems during planet formation. which makes 3i Atlas all the more interesting. It's not as ambiguous as Oumuamua. It's not as boring as Borisov. It's actively challenging our ability to explain it while providing enough data that we can't dismiss it as observational error or wishful thinking. The on-off cycling is real. The chemical anomalies are real. The X-ray emissions are real. Whether the explanation is natural or artificial, it has to account for all of these facts simultaneously. The implications ripple outward from there. If we're not alone, if the galaxy contains or contained other technological civilizations, then the universe is fundamentally different from the one we've been assuming we inhabit. It's not a sterile void with rare pockets of life. It's a place where intelligence arises, builds, explores, and leaves traces that persist across cosmic time. Those traces might be rare, spread thin across billions of stars and millions of years, but they exist, and finding even one would confirm that we're part of a larger story. If 3i Atlas is natural, the implications are equally profound. It means we don't understand comet physics as well as we thought. It means interstellar space can produce objects with properties and behaviors we never predicted. It means the diversity of small bodies in the galaxy is far greater than the diversity we've seen in our solar system. And it means future interstellar visitors might be even stranger, challenging our models in ways we can't anticipate. Either way, 3i Atlas represents a crack in our certainty, and through that crack, the universe keeps revealing that it's bigger, stranger, and more complex than any map we've tried to draw of it. The observations continue, the data accumulates, and we keep watching, trying to decide whether we're looking at a comet that breaks the rules or something that was never subject to those rules in the first place. So where does that leave us? Standing in the middle of December 2025, watching an object that shouldn't exist according to the rules we've spent centuries building, trying to decide whether we're witnessing a revolution in comet science or evidence of something far stranger. 3i Atlas continues its journey outward from the inner solar system, following a trajectory that will eventually carry it back into interstellar space. Whether it will reactivate again remains unknown. Whether we'll ever fully understand what we're seeing remains even more uncertain. The scientific process moves slowly, deliberately, carefully. Peer review takes time. Consensus builds gradually as multiple teams analyze the same data and reach compatible conclusions. What we have right now is raw observation and preliminary interpretation. The on-off cycling is documented. The chemical anomalies are confirmed. The X-ray emissions are detected. What we don't have yet is a comprehensive theory that explains all of these phenomena in a way that satisfies the majority of astronomers working on the problem. That theory might emerge in the next few months or years as more data accumulates and more researchers tackle the puzzle. Or it might remain elusive, leaving 3i Atlas as one of those objects that defies easy categorization. The history of astronomy is full of such objects. Things that seemed impossible when first observed, but later became understood as natural phenomena, operating under conditions we hadn't encountered before. Pulsars were briefly thought to be artificial beacons before we realized they were rotating neutron stars. Gamma-ray bursts were mysterious explosions before we connected them to dying massive stars and colliding stellar remnants. Fast radio bursts were recent additions to the catalog of cosmic mysteries, now gradually being explained through various high-energy astrophysical processes. 3i Atlas might follow the same path, from anomaly to understood phenomenon, once we figure out which natural processes can produce its observed behavior. But there's also a chance it won't. There's a chance that 3i Atlas represents something genuinely new, something that forces us to expand our understanding in ways that feel uncomfortable. Natural doesn't mean simple. Natural doesn't mean familiar. The universe operates on principles we're still discovering, and those principles can produce outcomes that look designed even when they're not. Complexity can emerge from simple rules. Patterns can arise from chaos. What looks like deliberate control might be an inevitable consequence of physics we don't fully grasp yet, or it might actually be deliberate control. The challenge is distinguishing between these possibilities without letting our assumptions bias the analysis. The uncomfortable middle ground is where we currently sit. We have evidence that something unusual is happening. We don't have definitive proof of what's causing it. We have multiple hypotheses ranging from exotic natural processes to artificial origins, and none of them are fully satisfying yet. This is normal in science, though it's frustrating for people who want clear answers. Real research happens in the ambiguous spaces where data and theory haven't fully aligned. Breakthroughs often come from sitting with that ambiguity long enough to see patterns that weren't obvious at first glance. What makes 3i Atlas different from earlier interstellar visitors is the quality and quantity of data. We're tracking it with better instruments, from more locations, across more wavelengths than we could with previous objects. That means we're seeing details that would have been invisible in earlier encounters. The on-off cycling might have been happening with Oumuamua too, but we wouldn't have been able to detect it with the observational cadence available at the time. Borisov might have had chemical anomalies that we missed because we weren't looking for them. 3i Atlas benefits from improved technology and increased awareness that interstellar objects can be strange. We're watching more carefully. We're measuring more precisely. And as a result, we're finding more things that challenge our expectations. The broader context matters here. We're living through a period of rapid discovery in astronomy. Exoplanets are being found at a rate that would have seemed impossible 20 years ago. Gravitational waves are opening new windows onto the universe. The James Webb Space Telescope is rewriting our understanding of galaxy formation. The Square Kilometer Array and other next-generation radio telescopes will soon start mapping the cosmos with unprecedented sensitivity. We're not short on mysteries to solve or phenomena to investigate. 3i Atlas is one puzzle among many, but it's a particularly compelling one because it's local, observable, and directly challenging models we thought were well established. The question of whether we're alone in the universe has haunted humanity for as long as we've been capable of asking it. Every culture has myths about beings from the sky or messages from the stars. The scientific search for extraterrestrial intelligence has been ongoing for decades, scanning radio frequencies for artificial signals, analyzing exoplanet atmospheres for biosignatures, calculating probabilities based on Drake equations and Fermi paradoxes. 3i Atlas doesn't answer that question definitively, but it adds a data point to the conversation. It reminds us that the universe is capable of surprising us, and that our assumptions about what's possible might be too narrow. If this object really is artificial, then we've already had our first contact. Not in the form of communication or intentional signal, but in the form of hardware. A machine passing through our neighborhood, doing whatever machines do when they're billions of years old and still functioning. That realization would be profound, not because it would tell us anything specific about the civilization that built it, but because it would confirm that such civilizations exist or existed. The universe would become a place where intelligence arises, builds, and leaves lasting marks. We'd be forced to reconsider our own trajectory and whether we'll eventually join the ranks of species that send their creations into the void, hoping something out there will notice. If it's not artificial, if 3i Atlas is just a really weird comet, then we're being reminded that nature is endlessly inventive. The physical laws that govern matter and energy can produce outcomes we haven't predicted, behaviors we haven't modeled, structures we haven't imagined. Comets might be more diverse than our solar system examples suggest. Interstellar objects might regularly exhibit properties that seem impossible based on our local sample. The universe might be full of things that look artificial, because natural processes can be that strange. either conclusion fundamentally changes how we approach the question of what's possible. So we keep watching. Telescopes around the world and in space remain pointed at 3I Atlas as it moves farther from the sun. Researchers continue analyzing spectra, tracking position, measuring brightness. The data accumulates slowly, building toward whatever understanding we'll eventually reach. Maybe that understanding will come quickly, a sudden insight that makes everything click into place. Maybe it will take decades, requiring new theories and new observations and new generations of scientists approaching the problem with fresh perspectives. Maybe we'll never fully understand it, and 3I Atlas will remain an enduring mystery, a reminder that the universe doesn't owe us explanations. What we can say with certainty is that we're witnessing something remarkable, an object from beyond our solar system, exhibiting behavior that challenges our models and forces us to question what we think we know. Whether it's a harbinger of stranger discoveries to come or an isolated anomaly, it's doing what the best science does. It's making us uncomfortable. It's pushing us to think harder and look more carefully and admit when our current frameworks aren't adequate. And somewhere out there, beyond the orbit of Mars, moving steadily away from us on a path determined millions of years ago, 3I Atlas continues its journey, pulsing, cycling, doing whatever it does for reasons we can only speculate about. Indifferent to our confusion and our theories, and our debates about whether it's a comet or a machine or something we don't have words for yet. The universe, as always, keeps its secrets, and we keep trying to read them in the light of distant objects that refuse to behave.